I'm going to take my mask off. I hope that's all right. It's certainly fine for everybody online. So I decided to rename my talk to call it Waves, Waves and Gravitational Waves. And I've just got a few introductory slides. The first one is our research centre up at Gingin. The research, the gravitational wave research takes place at that and the top left-hand corner of the slide, where there is a gravitational wave interferometer system. The foreground is the Gravity Discovery Centre, which was an education centre that we set up many years ago now to try to involve the public in the process that we knew was going to happen, which was the successful detection of gravitational waves. But this was set up 15 years before that happened. And at the middle left, you can see the Zadko Telescope Observatory. And on the right, of course, you can see our famous Leaning Tower of Gingin. I hope a lot of you have been there, and if you haven't, I want you to know that it's open 7 days a week, and it's fun, and they have great astronomy nights as well as educational stuff and bushwalks and all sorts of things. So, so that's the first little bit of context. The second is our Centre of Excellence for Gravitational Wave Discovery. And one of the main things that we're working on now is designing better gravitational wave detectors for listening to the ripples of space, which are gravitational waves. I won't be saying too much about that, but just alluding to some of the some little details. But as Hugh mentioned, we have this other project, which is called Einstein-First. It's great having two members of our team here today. And it's the same motivation as the motivation for building the Gravity Discovery Centre, which was that everybody's got the right to share our best understanding of physical reality. It's not something just to be confined to scientists, it should be for everybody. And we think it's particularly important now because children are losing interest in science and Australia is falling behind in STEM. And we believe that we have the solution, and that is Einstein-First, which is introducing modern ideas of science at a very early age, at the age that kids often hear about it through the media, but they don't ever hear about it from their teachers. So I'm going to be mentioning, at least, and the context of all of this is 6 types of waves. Ocean waves, because ocean waves generate the microseismic waves that are a big problem for us, and we've got to do something about them. And I'll say a little bit more about that. And the seismic waves themselves, which are not just due to the ocean, but due to all sorts of things, are all part of that problem. The other part of our problem is phonons, which are quanta of acoustic waves that include heat, and we do all our detection using photons, which are quanta of electromagnetic waves. But we have to take into account probability waves or matter waves. We have various ways of describing these things, but there's some sort of conceptual or mathematical waves, but they determine the quantum probability of finding things at a particular location. And that is critical for us. And then finally, is the whole purpose of this, which is gravitational waves, as I said, in the fabric of space. Now, I'm going to be using some of the child-friendly language that we have been developing for our Einstein-First project. We try to avoid technical language and find things that evoke the ideas. So if some of you come back and said, no, you're not using, that's not a very good word, I'll be pleased to hear that, because it's always hard to find the best way to tell the story. But Einstein's gravitational waves were long thought to be undetectable, but to do the detection, we had to take into account many things, and in particular, things that people normally imagine to be rigid are wavy, and things imagined to be wavy are what we call bullety. And we use the word bullety because bullets can impart momentum and they can also break things, and that's what bullety photons do, for example. So they were always thought by Einstein to be undetectable because the size of the displacements that we had to measure are about 10 to the minus 20 meters, the number you can see sitting in the middle of the screen. On the right, you can see a piece of apparatus, and the apparatus consists of mirrors and vibration isolation systems, and I'm not going to go into a lot of the technical details, but let's just first of all look at these things that we might have imagined to be rigid and are not. And the first is the elastic properties of space-time, which is the basic idea of general relativity. It has a spring constant, which is given by c to the fourth over 8 pi g. Now, we all know c to the fourth, speed of light to the fourth power, is a gigantic number. Divided by the gravitational constant, and it's even more gigantic. That is how stiff space-time is, 10 to the 30 times stiffer than diamond. So, but it is still elastic. Then something normally thought to be rigid and so pretty absolute is something like the 40-kilogram mirrors that you can see in the image just there. But we have to take into account their waviness as well. And that really sets that limit. Again, it's around about 10 to the minus 20. If that constant K was much smaller, that number 10 to the minus 20 wouldn't be so small, but it's small because of the stiffness of space. And finally, we've got to take into account the bulletiness of light, and that is absolutely fundamental. So we had to develop all sorts of wave technologies to do all this, to make it work. And the first is, I've just put them in a relatively arbitrary order, but the sort of order I had in the previous slide. The ocean waves induce microseismic waves. They produce a microseismic signals of about 1 micron amplitude, 10 to the minus 6, but we're trying to measure 10 to the minus 20. So there's 14 orders of magnitude discrepancy. We have to do something about that. What we have to do is sense, image, and suppress those seismic waves. Up at Gingin, we've got a seismic array, an imaging array for imaging the seismic waves so that we can know what the seismic amplitudes are at different locations in the site. We're still in the process of developing that, and we'd be very pleased if anybody would like to join our collaboration to do with this imaging of gravitational waves. One of our members of our team, I think, is the next speaker in this session, Erding Sagan. The third thing is we have to have acoustic wave attenuation systems. Acoustic waves are typically about 10 to the minus 10 meters. So we've got to go from 10 to the minus 10 to 10 to the minus 20. That again is something enormous. What you can see in the picture on the right is just the very bottom end of a multi-stage vibration isolation system that is particularly designed to keep acoustic waves out. Then we have to deal with ultra-low acoustic loss materials. And acoustic loss is something that bothers us all the time. The mirrors that you can see especially the bottom mirror in the image on the right has got ultra-low acoustic loss, and it has optical coatings on it with the lowest acoustic loss we can get. In fact, the loss in the optical coatings, the acoustic loss in the optical coatings, is one of our critical limiting factors. And this is pretty astonishing. When seismic waves pass, or when infrasound passed, which is often generated by ocean waves and storms and things like that. Those are pressure fluctuations and density fluctuations. And a density fluctuation has got a gravitational influence. The gravity is fluctuating. And that gravitational fluctuation at low frequencies also comes in around 10 to the minus 20 meters. So we have to be able to measure the seismic waves so that we can subtract that out. And that's going to be particularly important for the future. And then finally, but absolutely central to our detectors, and I'll say more about this, is we deal with optical standing waves and state-of-the-art optical technology. And that is how the measurements get made. So that's a sort of overview. And here is a picture which was made about 2015, 2016 at the time of the first discovery. And I have a little bit of audio with this one. Two black holes far away in the universe that spiraled together, created ripples in space-time. Those ripples in space-time traveled through the universe until they'd reached this L-shaped gravitational wave detector. And there at that detector, they imparted a tiny bit of signal, a tiny bit of vibration, and what we heard was something like this. We only heard one of those. You heard lots of repeats just to make it easier to take into account. But we heard just one of those, lasting for less than a second. But with that, it was sufficient to determine that we had seen two black holes colliding. And sometime later, a few years later, 2017, we saw two neutron stars spiraling together, and they created similar ripples in space. The chirps, which were those little beepy or whoops that you heard, last much longer because the masses were smaller, lasted for more like a minute. I'm not going to bore you with a minute-long chirp, but that's the sort of thing that we saw. Now, 2016 was the year that we were celebrating. We had just announced the discovery of gravitational waves, and Nature magazine obviously had an article about it, and they had this picture of a gravitational wave detector. And it shows a laser beam coming into a beam splitter, splitting off two ways, going 4 kilometers down a tunnel, coming back again, and great. Coming back again into a beam splitter. But I want you to notice that the language that is used in that is entirely classical. And it doesn't represent the reality that we know about optics and photons. A better way to do it will be to say we have a photon source, which is injecting lots of photons into this thing. We have a photon beam going one direction and back again, another one doing that. And we have photon detectors that can detect photons with 95, 99% efficiency. We have probability waves, which are coming out of that system, and the photon arrival probability could be nearly zero if the two arms were equal, and if there was a difference in the arms, then the photon arrival probability is non-zero. That is what we understand the quantum description of these things to be, and that is what we teach children about in primary school. So, I'm going to come back to this point some more. So I want to now really step back in time and show how all of this directly links to a whole stack of historical studies, discoveries, 12 by Einstein, 1 by Schwarzschild, and 1 by de Broglie between 1905 and 1924. I want you to see the connection because every single one of these discoveries is manifest in these gravitational wave detectors. But also, as you can see in the image on the right, this is the book we launched last year, Teaching Einsteinian Physics in Schools. We've addressed this book to school teachers, primary school teachers, and middle school teachers and high school teachers, so that they can understand this and make it, put it at the level that it can be taught in school. So let's just have a quick look at this history. And I've numbered all these things, at least the 1 to 12 for Einstein. The first one is light comes in energy packets called photons, and that everybody knows about that. The second was Brownian motion, which you often think about. Atoms make pollen grains jiggle that you see in a microscope. The third thing is that speeds add up in a relativistic way, not in a simple additive way. 90% of the speed of light plus 90% of the speed of light doesn't give you 1.8 times the speed of light. It gives you only something closer to the speed of light. Energy has mass. We all know that. E equals mc squared. At least everybody knows the formula. Most people don't know really what it means, but that's where it originated. And that, you'll see, is critically connected to what we're doing. And the speed limit of the universe. Nothing can go faster than light. That was particularly important in the context of what Einstein did in 1907. Because in 1907, he basically was focusing on three ideas. One is that heat comes in energy packets called phonons. Now, just remind everybody, the word phonon wasn't invented until 1930s. The word photon wasn't invented till 1924. It's also very funny that people didn't really quite believe any of this until there was good names for them. The good names had a big effect. Then the second thing is gravity disappears when you're falling. We often talk to children about the Model T Fords had just come out. Einstein was, obviously loved to get a ride in a car, feel the acceleration. That was when he realized that acceleration and gravity were indistinguishable. And then the third, but really important, was that Newton's gravity must be wrong, because Newton's theory of gravity says that it travels instantaneously. There's no time delay in Newtonian gravity, but that couldn't be right. So then there was about 9 years of struggle by Einstein. And then his genius idea came out. And that was the idea that space is elastic. And it's expressed as matter tells space-time how to curve, space-time tells matter how to move. If you know that, you know the essence of general relativity. The next year, Einstein said that if it can curve, should be able to have ripples, should be gravitational waves. I'll come to that again in a moment. The 1917, he said, well, photons are bunches of energy, but they must have momentum too. Now, I think that's not surprising, and it's actually a bit astonishing that Einstein even felt he needed to say that, especially because some of you work on ocean waves, and I'm sure everybody has enjoyed seeing an ocean wave crashing into a rock and an explosion of water going everywhere. Well, surely waves have momentum. We don't need to be, it's not really a surprise, but it was still a landmark in the physics. And same year, actually the same paper, he predicted stimulated emission. That's the physics of lasers. So there we have Einstein's 12 important discoveries. 1924 came the next really important discovery, which is what I call it's the great unification, which is the idea of matter waves. The formula, wavelength, is Planck's constant divided by the momentum. And that, the wavelength, is the wavelength of anything. It's the wavelength of anything with some momentum. It then has a wavelength. And true for light, but true for cricket balls too, or gravity wave mirrors in our detectors. So how do we express this for children? It's a fairly complex idea that people have taken a long time to understand, or we express it like this. Everything has waviness. Everything has bulletiness. Now, bullets you can count. So we say bulletiness follows the maths of numbers. Waves, it's rather tricky to work out how to combine waves. You've got to do some vector addition. We use phasors. And so we say waviness follows the maths of arrows. Waves you can have 1 + 1 = 2 if they're in phase. You can have 1 + 1 = 0 if they're out of phase. That's the maths of arrows. So we teach this at primary school. And Anastasia, who's here in the audience, is one of our pioneers in that area. Now, I just want to go back to Schwarzschild and Einstein. Schwarzschild I didn't mention, but he was the one who solved Einstein's equations within a month or so of receiving them when he was on the Russian front in the First World War. And he quickly, instead of calculating where bullets should go or where missiles or cannons or something would go, he decided to try and solve Einstein's equations, which is all he'd received. He found a solution, and he found a very strange solution that said that if something gets sufficiently compact, that its radius falls to twice the mass times the constant g/c², a very small number. You saw g over c to the fourth over g, the stiffness of space. Here you're seeing g/c². This small number, that sets, at that point, you have a black hole. Nobody thought this could have any connection to physical reality, but that was his solution. Einstein was impressed by the solution, but I think he didn't believe it could have any physical reality. A few months later, but by that time Schwarzschild was dead, Einstein found an equation for gravitational waves. And in a sort of simplified form, it looks like what you can see at the bottom of the screen. It's got another one of those constants like the ones you saw, but this time it's g/c⁵. That's a crazily tiny number. And times that tiny number, you need to have the mass squared, the size to the 4th power, and speed to the 6th power. You can put in planets going around the sun, or asteroids going around each other, or some funny shaped weights rotating, whatever you like, and you'll get, whatever you do, you get some ridiculously tiny answer because of that constant. But then our story sort of finishes until the 1960s, when people saw strange things in space, like you can see at the top right-hand side. Einstein was dead, and people could only interpret these things that there were actually black holes out there. The word black hole was only invented a few years after that. And then somebody, Freeman Dyson, did something which anybody could have done in 1916. We had that formula for a black hole, which just had some constants and a radius in it. It connected mass to size. You could have made a substitution, imagining your things were black holes instead of planets. And when you make that substitution, anybody can do it. It's really easy. You use Kepler's laws for, say, orbits, and then you find that the power is given by the formula you can see there in the middle. Notice the difference. The first one, Einstein's formula, had g/c⁵. This one has c⁵/g. What an incredible sleight of hand. You've suddenly increased the size of a number by 10 to the 104 or something. Well, but it's not a sleight of hand. It's simply that we recognize the existence of black holes. The other two things are, what's the speed compared to the speed of light? And when two black holes collide, they're colliding close to the speed of light. So that's a number of order 1. And the other is, what's the size compared with the radius of a black hole? Well, if it's two black holes, the size is about the same. So that number's 1. So the power is something absolutely crazy. It's 202,000 suns per second being turned directly into energy. If you work it through in more detail for, say, two black holes, you find that 5% of the black hole mass can convert into gravitational waves in the time that we were talking about before, say a tenth or 2/10 of a second or something like that. And that tells us that if black holes are out there and if these things are happening, then space must be full of ripples, just like the oceans are full of ripples, always full of ripples. So that was incredible motivation for experimentalists to say, then surely we can do it. If nature's given us so much energy, we must be able to detect it. And here is the story of detection, if I can make this video.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
At the end of that, you will have seen, David writes, he said, this is a simplified explanation, and the simplified explanation was that light was a classical wave. And I want to quote Richard Feynman, who says, I want to emphasize that light comes as particles. It's very important to know that light behaves as particles, especially for those of you who have gone to school where you were probably told something about light behaving as waves. And that's how it still is today. That was 50 years ago that he said that, or 40 or 50. So let's just think about what this means. So we have that 1905 discovery that light comes as photons. So what will happen to light at the beam splitter? if it was a classical wave? Well, it would have to be splitting the wave energy somehow. And if the wave energy depends on frequency, as we all believe it does, like Planck's constant, like Planck's equation, then photon energy would halve at the beam splitter, and the color of the photons would change. But we know that partial reflections in windows are not of different color. We know that that's wrong. And anyhow, Einstein tells us these things are coming as particles. So if light comes as photons, then what happens? Well, there's no way that you can envisage any way of a stream of photons coming to a beam splitter that could be deterministic, exactly half one way, exactly half the other. We all understand today that this is done by probabilities. So at the beam splitter, it's probabilistic. Now, there are beautiful subtle effects that happen at the beam splitter, which I'm not going to discuss. But the main thing is, the only thing that we can have is a probabilistic interpretation. And if that's the case, then it's like tossing a coin. Every photon that comes, you go left or you go straight. And as a result, there has to be randomness in those photon beams. And if there's randomness, then all measurements with light must have intrinsic noise. So straight from the discovery of the photon, that means there must be some noise. And it also means that the light beams can never perfectly cancel because they are not perfectly equal at the output. I want to go into that in a little bit more detail, because what it means, so imagine now you've got n photons coming in some period of time when you're trying to get a measurement, like in a gravitational wave detection is, say, a millisecond. How many photons arrived in a millisecond? Well, some vast number, but which we can think of as n. And then from statistics that we all know, from data analysis and all sorts of different things, the uncertainty goes as the square root of n. So if you want that uncertainty to be small, you've got to have a very large sample. N must be very big. And n photons with n a very big number means high intensity. So if you're going to get good measurements, you've got to have high intensity. But 1917, Einstein said photons have momentum. If there's a few more photons in one beam than the other beam, they are pushing and changing with time. They're pushing on the mirrors, and the mirrors will recoil. And there'll be a difference in the recoil between the two mirrors. As a result, the path lengths between the two arms of the interferometer won't be the same, and there will not be a dark fringe. But that number, those fluctuations get bigger. The square root of n, if n is 10 to the 20, the square root is 10 to the 10. That means there are 10 to the 10 extra photons, sometimes in one arm than the other. If I had 10 to the 30 photons, it would be 10 to the 15. It would be bigger. So, you mustn't have too many photons, or you have what we call radiation pressure noise, and the other one we call shot noise. And there's a graph that shows how you reach the standard quantum limit, which is basically the uncertainty limit when the quantum uncertainty principle limit, where you balance these two effects. And that limit happens to be round about for a certain amount of power and things, turns out, for big mirrors, like I was talking about, turns out to be this magic number round about 10 to the minus 20. So current research, and what we are very much involved with, is working out how to increase the intensity from about 50 kilowatts to around about 500 kilowatts, and also ways of manipulating the statistics to make it better, called squeezing. But I just want to give you another idea of how we can get these crazy amounts of power. We don't have 50 kilowatt lasers available, suitable for doing experiments like this, but we have 100-watt lasers or so. So you have something like the picture you can see. That would never detect gravitational waves. You've got to do something better. The first thing we do is we add 2 more mirrors and we make these into optical resonators. We resonate the light and build it up, just like you can build up the swing of a swing in a playground by lots of little pushing. We build it up, but that's not good enough. Remember, we'd like to be at a dark fringe, very close to a dark fringe. That means nearly no light comes out. If nearly no light's coming out, it means all that light's going back to the laser. What a waste. Don't waste it, recycle it. And so we put in a recycling mirror to send that light back in and make the whole thing into a resonator. That way, we can reach about 0.5 megawatt in principle, but in practice, we can't do it. And I'll say a little bit about that because that's interesting quantum physics too. But we do one other trick, one more trick done with mirrors, and that is add another mirror here. We call it a signal recycling mirror. Resonate your signal photons and you can build up the signal a little bit more. So this amazing pattern of mirrors lets us build a detector that in principle could get to 10 to the minus 20 meters. But I want to now just say a few things about waviness and measuring size of things. And this came up particularly because I heard somebody saying the other day, electrons are the teeniest, weeniest things around. And I said, no, they're not. They're the size of atoms. And because in an atom, what we see is the wave function. And the atom, I just want to keep track of the time. Yeah. In an atom, what we see is the standing wave of electrons, and there is a particular standing wave of an electron, and that is set by the scale of the waviness of the electron. And so I've been calling this wavelength size. The wavelength size is the size of an electron. Now, if I put my electrons into an electron microscope and give them more momentum, then I can reduce the wavelength size. And that's how electron microscopes can see down to atomic dimensions and even below. But in CERN particle accelerators, I can give them the most crazy amounts of momentum and collide them together, and still you never pass the wavelength size. So they're actually unmeasurably small. The intrinsic size of an electron has never been measured, but the size we observe is this wavelength size. And that's a reality for us. In a gravity wave detector, you can say, how big is a gravity wave detector? Well, it's 4 kilometers. And it's got mirrors, which are 40 kilograms. But where does wavelength size fit into this? This is the wavelength contribution of the test mass itself. And that is about 10 to the minus 20 meters. So the waviness of the test masses is effectively our limit coming in around 10 to the minus 20. And of course, then you might we try to measure size with photons, and the size of a photon is roughly its wavelength, but we can measure better than that because we can take averages and then we can do it wavelength divided by the square root of n, and that gives us this huge laser power we need to get to 10 to the minus 20 meters. So that's the basic quantum physics that gets us to this magic number. Now, I've got one slide to tell the story about why it's hard to get to this very high power. And this is about more quanta. So we take our laser beam and we put it into the optical cavities that you've seen. But we expand it so that the beam is averaging over lots and lots of atoms, because we know the size of an atom is 10 to the minus 20, 10 to the minus 10 meters, typically. So we got to average over all the atoms in the surface of our mirrors if we're going to get anywhere. That means we have to have big, big beams. And so we send in a big beam that we call a Gaussian beam, which is the incoming photons. And so you can think of these photons as sort of flat pancake-shaped things with an increasing density into the middle, like you can see. But then they hit the mirror, and remember Einstein's discovery number 2 in my list? It was Brownian motion. Atoms vibrating things. Well, those atoms are vibrating these mirrors. And this Brownian motion of the mirrors would be a terrible problem unless we could make all of that vibration occur in only one frequency. And we can do that if we can make them into acoustic resonators that have got extremely narrow line widths. So all the vibration happens at their own frequency. That's why we have to have fantastic acoustic materials. But still, they've got these modes of vibration. And there's a typical mode of vibration of that mirror, which might be occurring at, say, 40, 50 kilohertz. That scatters these pancakey shaped photons that are hitting that mirror and converts them into a pattern of what we call a high transverse mode photons. And those photons look just like the acoustic photons. And if that cavity can sustain the resonance of that frequency, which requires particular conditions, then you have a process happening which you can really only understand simply in a quantum mechanical form, which is the square box on the right-hand side. It's a simple scattering process with photons of a certain energy are turning into photons of a lower energy, and in the process producing phonons at another frequency. And because you've got a huge intensity of these photons going into the thing, it's a one-way process that drives the whole system into oscillation. We predicted this in 2010, and we said the LIGO detectors will never work because of this problem. They were trying to commission them in about 2014, and we had spent many, many years trying to study this phenomena because we knew it was a serious phenomena. Everybody else was ignoring it because they didn't really like the bad news. But then when they were trying to commission the LIGO detectors and they started whistling and losing lock, as we call it, and all falling apart, we were able to say, we know how to help you. And we sent somebody over there and they worked with them, and we managed to work out enough control that you could get to 20 kilowatts. Remember, we'd like 500 kilowatts. We could get to 20 kilowatts, but that was enough for the first detection. And our person was there at the time of the first detection. And so that's our claim to fame. So that's just one of the many, many issues in gravity wave detectors. So let's quickly go through 6 years of discovery. These wave bursts we saw coming through the solar system, you saw some imagery of that in the video, that wave burst in terms of energy flux was greater than the energy flux of any astronomical phenomena that's ever been observed by modern astronomers. And since then, in 6 years, we've seen 90 of these bursts, roughly. So imagine this huge thing. And that was this huge amount of energy after it had traveled for more than 1 billion years. So it had been distributed throughout the universe, and yet what arrived here was still brighter than anything else. It was coming from distances beyond which stars can be seen in telescopes. You can see galaxies, but you can't see the individual stars. What we found out were these were black holes between 10 and 1,000 kilometers diameter. And doing a little bit of simple statistics, very rough, we're able to say that these things must be merging in the universe about every few minutes. But we can only see the closest ones. Then we saw these neutron stars coalescing, and when that happened, it gave out a vast burst of gamma rays. And the gamma rays, and then there was light. which was seen by telescopes first in Chile, then the Zadko telescope here, and many, many telescopes in the world. And they saw the light, we saw the gravity waves, and the difference between the gamma rays and the gravity waves was 1.7 seconds. The travel time had been 150 million years. So we could say that the speed of gravity waves was the same as the speed of electromagnetic waves in the form of gamma rays, to 1 part in 10 to the 15, roughly. So Einstein was right. But from the light, we could see evidence for heavy elements, and a mystery which has been not very well publicized in the past had always been astronomers couldn't explain where all the gold and other things came from. Well, and plutonium and lead, all those heavy elements, because they're not energetically favored. It has to happen very fast. Well, when two neutron stars come together, they're pure neutrons, and some remnant, when the pressure is removed, when the two remnants are almost touching, gets out into space and basically explodes like a gigantic atomic bomb. And just as atomic bombs make a bit of gold and many other elements, so does this. And that's where, so if anybody's wearing a gold ring, that was made in a neutron star coalescence, probably a billion years, or 5, 6, 7 billion years ago. So that was a wonderful discovery too. And I mentioned the light speed. And in 2020, we saw black holes swallowing neutron stars, just 2 of those. So now I mentioned E equals mc squared at the beginning. I just wanted to show the specific evidence that we had here from the very first event. One black hole, 29 solar masses, one was 36 solar masses. They spiraled together, creating this chirp signal that you heard. And the final black hole was 62 solar masses. There's a discrepancy if you add those up. That was the mass of the gravitational wave energy, E equals mc squared, emitted. And at the time of coalescence, those stars were going at about 0.6 of the speed of light. And here's a visualization of one of these things when the mass is not so equal. And this is more like the neutron star black hole situation. The picture shows 2 black holes, but you can see what happens. The frequency rises slowly, but the faster it goes, because the energy output depends on speed to the 6th power, it all finishes very, very rapidly. And there you can see that rapid finish, and even in slow motion, it's rapid and also a little bit boring. You know, you don't see anything very wonderful happening. You don't see wormholes being produced, for example, as I was discussing with Anastasia when we were coming over here. If wormholes were real, which I don't believe they are, we might have seen them in that situation, and we don't. So that's just a graphic about the neutron star black hole coalescence made by our Center of Excellence. And now here's just a little summary of some of the events that we've seen. And just to explain this picture, what you see is pairs of black holes with certain masses. The masses are up the left-hand axis. And then they're just in arbitrary positions just to make a nice, pretty picture here. And you see, so the far left one, you've got fairly close to 20 solar masses making around about 40 solar masses. You see some of the biggest ones in the middle, but the ones that were really fascinating because we really knew they ought to be there and we never had seen them was a case where something came from the neutron star mass band, which is less than 2 solar masses, and it combined with something that was 5, 6, 7, 10 solar masses. That was a black hole eating a neutron star. So we were very pleased about that, which came out last year. So just think again, coming to the end, about these vast but imperceptible explosions. You could be pretty close to one of these things and it wouldn't bother you. But the energy release was something like 10 gravitational energy. The signal flux was about 10 to the 5th times the brightest star in the sky, Sirius. The detected signals were the smallest amount of energy ever measured by any instrument on Earth. The travel time is typically 1 to 3 giga-years. And that means we're seeing far, far away into the universe, but we're not seeing back to the Big Bang where you have to go way past 10 giga-years. But you're not too far away from the Big Bang. And the Earth's distortion, well, Australia shook by the size of a proton, roughly. And in 2019, the Event Horizon Telescope actually managed to image a gigantic black hole about 10 to the 9th solar masses. And I just want to mention the fascinating optics around black holes, because you can see the back of them. And this is the sort of distortion of a disk that you will see if a disk happens to be around a black hole, as we think there are many of in the universe. Here's our latest catalog, which is you can count all of the black holes. It's not a very exciting picture, so I'm not going to waste your time on it. But for every pair of black holes, you can look at what were the masses and what was the final mass and how much mass in gravity wave energy was emitted. Black holes, as everybody knows, I think, time slows down as you get close to a black hole. And gravity waves have some difficulty escaping from black holes for the same reason. Some energy is lost. And all of this time warping is really significant. This is just a picture from our Leaning Tower at Gingin, where as you climb the tower, you see how you are climbing through a time gradient, and you're managing to, achieve 5 microseconds per century. You're changing your lifetime by 5 microseconds per century in a sense as you do that. But the Earth slows our aging about 1 second in a lifetime. And Richard Feynman long ago pointed out that the core of the Earth must be about 4 years younger or 3 years younger than the surface for the same reason. We know that space-time has a beginning and an end, and this is, how we might do this with school kids. You can't see we probably can never see the beginning of the universe, but we can see the end of space-time when 2 neutron stars merge to make a black hole. And that is the plan. Oh, I don't think I have time to show you this slide. It's a lovely slide, but I'll have to take ages to tell you. But this is about playing the whole universe, all the history of the universe simultaneously when you're observing with slightly better detectors than we've got today. And the message here is that OzGrav is planning to build the NEMO gravitational wave observatory, which is intended to see that process where neutron stars actually turn into a black hole. We didn't see that. We lost sight of it once the neutron stars had got very close. But we didn't see the actual process, what happens to the nuclear matter. This stands for nuclear extreme, or neutron star extreme matter observatory. So my concluding slide is just this. We had to harness our knowledge of all types of waves to make measurements close to these fundamental limits. The NEMO detector and other next generation detectors will be able to hear the whole of the universe, not just the nearest 3 giga light years. We'll be able to observe space and time come to an end when neutron stars turn into black holes. And in terms of education, we're trying to implement our exciting program that goes from year 3 to year 10 for all school kids. We're trying to implement that across Australia to reclaim science education. And the reason why we're doing it is that we think the world's future depends on science literacy, and anti-science movements are born out of the obsolete, boring, and irrelevant science taught in schools today. Thanks very much.
Thanks very much, David. So we can take a couple of minutes for questions. We started a little late. Are there questions from online? Okay.
Yep.